Okay, so last time we looked at this idea. Listen, we looked at the idea of, does it make a difference if a person driving a car is using a cell phone or just talking to somebody in the car with them? Okay, so we looked at how many times they missed an exit that they were supposed to take. So we got these numbers from the driving simulation that was presented in this problem. And we found there was a big difference because 29.2% to 8.3%, we said that's a big difference between those two. So we said statistically significant is when the difference is more than what we would expect due to random chance. So if you didn't write that in, please do so. So the difference is more than expected due to random chance. That you can kind of think of that as the difference between subjects. There's going to be some natural variability between people. The statistically significant is more than that. Okay, so it's more than what, it's just different because different people were doing this. Then we went to the inside, we did our card simulation. So we looked at a deck of playing cards and we decided that the 9 face cards were the drivers who missed the exit, and 39 non-face cards were people who didn't miss the exit. And that's what we used to do our experiment. Okay, so then we simulated this. So we took these 48 cards, mixed them together, shuffled them together, and then just dealt them into 2 stacks. And then you counted what was the percent of the face cards in each group and found the difference. So that simulated what we did on the front side. That simulated this 29.2% difference. And we wanted to know how likely is it to get this big of a difference, okay? So what I did was I took the data from all 3 classes and combined it together. So let me show you what that looks like. Okay, so hopefully you can kind of see. Each of these dots represent one of the simulations. So we see a large group of them right here in the middle. So this is at 4% difference. So hopefully you saw that when you were doing your simulation. You were getting a lot of these difference of 4%. This is the -4, which happened pretty often too. And then this is the 12.5. That happened a lot. And so we see a lot of these in the middle. Here, this is that 21% and more, okay? So this is how many out of all the groups. I have a little over 200 dots represented here. So this is about, I think it was 12 dots over here out of the, I think it was 215 altogether. So we had 12 out of 215 that got these results of the 29.2 or more. So the difference between them was 21. So here's the thing though. One of the ideas of this experimental design was randomization. In one of the classes, I did not give them any instructions for that and said, okay, just do this 10 times, and I didn't give them instructions on how to shuffle the deck and how to do all that. So let's see what it looks like without those in here, because I want to see, does it make a difference? So when I do this, this is without that class. So this ended up being 172 different trials that was done. So here we'll see this out here at the end, there are not many of them. So So when we took out that idea of you have to shuffle in between, then we had even fewer that were those extreme differences between the two groups. So we're seeing here was 8 data points out of the 172. So when we look back at our numbers here, we want to know, based on the class results, how often does the difference as large or larger happen due to random chance? So it happened 8 out of 172 times. I haven't done that calculation yet. So that's about 4.7%. So about 4.7% of the time, we're getting a value as big of a difference or more of a difference than what happened in that driving example. So what that tells us is that if there really were no difference, if it truly was, if it didn't matter whether they were driving using a cell phone or driving with the passenger in the car, if there were no difference in them, the probability of getting the results we have or more extreme is 4.7%. Okay, so the way we're going to look at this is go, is this likely? If something happens only 4% of the time, are you going to think that that's likely to happen? No. It's pretty unlikely. So were these results based unusual based on what happens due to chance? Yeah, because this only happens less than 5% of the time. So, yes. Get these results. Less than 5% of the time. By random chance alone.
There are certain numbers that are that.
Oh, I'm so glad you asked that. Let me finish this thought and then I'll get back to that because I love that question. So in other words, if cell phones had no effect on missing the exit. So, the question was, is there a value at which we go, okay, this is now unusual? Okay. Yes, but that number depends. Depending on what you're dealing with, you'll set a different value. So, in other words, if we're talking about something that's a life or death thing, then we're going to set this number is going to be a little more extreme. Because what this says, 5% of the time, this is normal. 95% of the time, this is unusual to get these results. So it's saying, if it really were okay, if there were no difference between them, 5% of the time, we would have been making this decision wrong. Okay? So it goes into what are going to be the consequences of saying this is unusual if it really wasn't. Okay? So those things, it depends on the situation as how much of the time you're willing to make that mistake. So it kind of depends. Usually, in order to reduce the amount of times you're wrong, you increase the sample size. Okay? If we get more and more of these, if I had 500 simulations, we would have a lot better idea of how likely it is based on more simulations. But in a real world situation, that costs money. Okay? If you're doing a drug trial and you look at 50 patients or you look at 500 patients, your cost is going to be a lot more having more people involved, right? Because you're having to supply all this medication for them, you're having to pay people to administer the treatment, you're having to pay people to collect the response variables, you're having to do a lot of stuff. The more people involved, the larger the sample size, the more expensive. But if it's something that's a life or death thing, if you're checking to see if you think you have the cure for cancer, it may be worth investing that extra money to make sure you're correct, versus if you're just trying to do something that's, predicting somebody's favorite color. Okay, well, we don't have to be as precise with that. We're going to get close to a lot of people like this, and we're okay with that. But if you're looking at some life or death treatment, you want to make sure you're getting it right. Okay? You don't want to give people a treatment and make them think they're getting better when they're really not, and you may be harming them more than helping them. So, yes and no. Typically, we look at either a 5% or 10%. If it's lower than 5%, usually we say that's unusual. Sometimes we look at 10%. If it's lower than 10%, then we call it unusual. But 5% is kind of the one we use most often. Good question. Anybody else? Questions? Okay. So the other thing I wanted to make sure we talk about, because this will come up on your test next week as well. This idea of drawing a conclusion from what we've done. So we can look at an experiment. You should, at this point, be able to look at an explanation. You should be able to decide what is the experimental unit, what are the treatments, what is the response variable, how did the randomization happen. You should be able to pick those things out of it, right? You guys are feeling good with that, hopefully at this point. You've already taken a quiz over it. The idea is whenever you are drawing up that experiment, if they say to you to tell how an experiment would be done, typically what you will do, you will start with something over here, you randomly assign them to some treatments, then you compare a response variable. Okay? So usually we do this all in context. We explain our experimental units in context of the problem, our treatment, and then compare response. Okay, so you should be doing something like this in context of the problem, and of course writing where the randomization happens. That should be a part of each one of these that you draw up a design. This idea of conclusions, your conclusion based on this comparison can only be applied to this type of subject. Okay? So if we are doing an experiment and all of our experimental units are high school students, we can only apply our results to high school students because those are the only people that participated. We can't apply it to adults or children. We can only apply it to the type of people that are the experimental unit. Okay? So you may have a question like that where it says, this is what happened, to whom could this be applied? And you have to know, whatever your experimental units are, that's what has to match your application of those findings. Okay? So let's look at an example. Hopefully you can kind of read it. So this says, so people who race greyhounds give the dogs large doses of vitamin C in the belief that the dogs will run faster. Investigators at the University of Florida tried 3 different diets in random order on each of 5 racing greyhounds. They were surprised to find that when the dogs ate high amounts of vitamin C, they ran more slowly. Okay? So, what are the experimental units here? All greyhounds? Just the racing greyhounds, right? Because all 5 that were tested were racing greyhounds. So that's where, remember how I was telling you, be as specific as you can when you're describing your experimental units, because every dog in this test was a racing greyhound. That means these results can only be applied to racing greyhounds. Does that make sense? Because those are the only people we tested. If it was a greyhound that wasn't a racing type greyhound, they may metabolize things different. They may have different reactions to things. We can only say these results would apply to racing greyhounds. Okay. What is the explanatory variable, or the response variable? Sorry. The racing speed, right? We're trying to compare how fast these greyhounds are. Good. What is the factor? Right. It's the diet that they're feeding the dog. So how many levels were there? 3, because 3 different diets. So 3 levels. How many treatments? If there is only one factor, the number of levels is the number of treatments. That was kind of a trick question. But since they only changed the diet, the 3 different levels are the 3 treatments. Okay. Does this make sense to you? You're going to see questions about this on the test. To whom could these results be applied? And you may be asked, could it be applied to all dogs? Could it be applied to all greyhounds? Could it be applied to all racing dogs? You need to make sure that you pick as specific as the question was. That's how you need to match it up. Okay? Good. Okay, so this one says, a researcher has designed a medical experiment to investigate whether a calcium supplement in the diet will reduce blood pressure of middle-aged men. Preliminary work suggests that calcium may be effective and that the effect may be greater for African American men than for white or Hispanic men. 40 randomly selected men from each ethnic category are available for this study. So first of all, let's look at this study. What type of design would this be? What is that? Blocking. Right. So this is randomized block design. What are they blocking on? The ethnic groups, because they think that may make a difference. Okay. What are the experimental units? Middle-aged men. Okay. So to whom can this be applied? Middle-aged men. Okay? So it's whoever we have in our experimental units. What is the response variable here?
Blood pressure.
Right. Because we're trying to reduce blood pressure. That's what we're comparing here. Okay? And the explanatory variable, or the factor? Calcium supplement. Good. Good. Is this making sense? Are we seeing it? Okay. So, what I want to do, we have about 10 minutes or so left. What I'm going to have you guys do, tomorrow, we have our first notebook check. So, I'm going to give you guys the next 10 minutes to make sure everything is ready for that. Which means everything needs to be attached. It should pass the shake test. I shouldn't be able to shake it and have things falling out at me. Everything should be attached. All the problem sets should be completed. All of your frappies, your multiple choice Mondays should all be in the correct place in the back. Those should all be completed as well. So take a few minutes, make sure that is done. I'll put the table of contents back up here, so we'll have that. That does not make it. That's just a checklist of things you need to make sure you know for the test next week.
From office to office. Back to building 6. So I was talking all of this, and I think I'm trying to switch from this
Yeah, if you can just get somebody to do
Okay. They